On day 3 of section 2.3, what I specifically want to talk about is those higher order derivatives. We mentioned the other day and we wrote down their notations. So we wrote down the notations of second derivative, third derivative, fourth derivative. We can take a derivative as many times as we wish. Most of the time we're going to talk about just second derivatives. So the first example I'm going to give you is just one of a second derivative. In order to be able to take a second derivative, you first have to have the first derivative. So we will go ahead and find the first derivative of secant x. We were to memorize those trig derivatives the other day. So those derivatives, one of them is secant x, and the derivative of secant x is secant x tangent x. Now that you have the first derivative, you are now able to find the second derivative. The second derivative requires the product rule. Notice my notation for the second derivative, f double prime. To take this derivative, then, we simply say to ourselves, the first, which is secant x, times the derivative of the second. The derivative of tangent x is secant squared x, plus the second, which is tangent x, times the derivative of the first. The derivative of secant x is secant x tangent x. I could leave my answer in this form, but I will go ahead and take the time to simplify this. This simplifies into secant cubed x plus secant x tangent squared x. That is as far as I am able to take this simplification, or this being able to simplify. This next problem, it starts out by saying to find the higher order derivative. It gives me the second derivative, and I now have to find the third derivative. So in order to find the third derivative, all we need to do is take the derivative of the second derivative. Notice the notation I'm going to use for the second derivative is the f double prime. I am going to go ahead and rewrite the second derivative with a negative exponent. That way, it does make finding the third derivative much easier. The third derivative then is f triple prime. And I'll take the derivative of the 2, which is a 0, so I will not write that. And then I will take the derivative of the negative 2x to the negative first by multiplying negative 1 times negative 2, which is a positive 2. And then I will lower the exponent by 1, which gives me a negative 2. F triple prime simplifies to be 2 over x to the second. The last part from day 3 will be the problem about velocity and acceleration. The first thing I want to talk about is how they are related. In previous lessons, we have learned that s of t stands for the position function. We also learned in previous lessons that the derivative of the position function equals the velocity. Now, this lesson, we're going to learn that if I take the second derivative of the position function, which would be the first derivative of the velocity, that equals my acceleration function. I need to know that before I can complete this problem. The first question in this problem is to find the velocity of the object when t is 3. I can do that simply by just plugging 3 in for t. I was given the velocity equation, so I can just go ahead and plug in 3. So the velocity when t is 3 ends up being 36 minus 9, which is 27. The label for this is meters per second. Velocity is always feet per second, meters per second, whatever label we're talking about, so distance over time. What I just got through saying was that if I took the derivative of the velocity, I would end up with acceleration. So that's what I'm going to do. I'm going to take the derivative of the velocity, which equals my acceleration function. The derivative of 36 is 0, and the derivative of negative t squared is negative 2t. I'm going to find the derivative at 3, or the acceleration at 3 by plugging in 3. I end up getting negative 6, and the label for acceleration is always meters per second squared. I shouldn't say always meters per second squared. I should always say it's distance over time squared. The last part of this question asks me, what can be said about the speed of the object when the velocity and the acceleration have opposite signs? In order to answer that question, I'm going to bring up my other slide. On this slide, it talks about how acceleration and velocity are related. So if I have positive acceleration and positive velocity, I know that it's getting faster in the positive direction. Negative acceleration and negative velocity tells me it's getting faster in the negative direction. Positive acceleration and negative velocity tells me it's getting slower in the negative direction. And negative acceleration and positive velocity tells me it's getting slower in the positive direction. So if I go back to the problem that we are working on, you can see that I have positive velocity and negative acceleration. Having different signs always leads to going slower. So I know that this is getting slower. In which direction? The direction depends on the velocity. So it is getting slower in the positive direction.